Hi all, this is Vijay Lakshmi. So today I'm going to take the topic of computer organization. The topic is Flynn's classification of computer architecture. So here we are going to understand the instruction of data streams in parallel computing. Here we have the introduction to Flynn's classifications. Flynn's classification was introduced by Michael J. Flynn in 1966. So it is categorizes computer architectures based on the number of instruction streams and data streams they can process simultaneously, which is helps in understanding the different levels of parallelism in computer systems. So here we have the key terms of instruction stream, which means the sequence of instructions executed by the processor. Next one is data stream, the sequence of data processed by the instructions. Next, moving into the categories of Flynn's classification. Flynn's classification divides computer systems into four categories. One is SIMD, which means single instruction stream, single data stream. Second one is SIMD, single instruction stream and multiple data streams. Third one is MISD, multiple instruction streams, single data stream. Fourth one is MIMD, multiple instruction streams, multiple data streams. The first one is SISD, which is single instruction stream and single data stream. Here we have the definition of SISD is a traditional architecture where a single processor executes one instruction at a time on one single stream, which means one instruction operates only one data element at a time, which is having the characteristics of sequential execution. Here we don't have any parallelism, which means no parallelism in terms of instruction or data. So example is early single core processors. So it is the traditional architecture where a single processor executes one instruction at a time on a single data stream. So let's move on to the next category, which is SIMD, single instruction stream, multiple data stream. Here we have the definition of SIMD is a parallel computing model where a single instruction operates on multiple pieces of data simultaneously. So we have the characteristics of SIMD is one instruction applied to multiple data elements in parallel, which is efficient for operations that require the same computation on large data sets. For example, matrix multiplication. Here we have parallelism also, which is data level parallelism. And examples for SIMD is graphics processing units for rendering, GPUs, and vector processors for scientific computing. So comparing to SISD and SIMD, in SISD, the traditional way of doing things, which means it is simple and effective for basic tasks like on early personal computers or microcontrollers. So in SISD, we have the example that is single worker who can only process one job at a time. But in SIMD, we still have one instruction, but it can handle multiple pieces of data simultaneously. So this is great for tasks where the same operation is applied to many data points like image processing. For example, a GPU in your computer processes millions of pixels at once when rendering graphics. So it applies the same instruction to many data points. This is SIMD in action. So next is MISD, which is multiple instruction streams, single data streams, which is a bit strange and frankly not very common. Here you have multiple instructions operating on a single piece of data. So the definition is a theoretical model where multiple instructions operate on the same data stream. So here we have the characteristics of MIST, multiple instructions on a single data element. Uncommon in practice, no significant use cases in general computing. It could be used in highly specialized systems for redundancy or fault tolerance. The fault tolerance, which is nothing but the ability of a system to keep working even when one or more of its components fail. It is very important for systems that are mission critical or high availability or life critical. So this type of system is mostly theoretical. It might be used in some fault tolerant systems, I said, where you run multiple checks on the same data to ensure reliability. In general, you won't see MIST in most modern computers, but it has nice applications. So the next one is MIMD, multiple instruction streams, multiple data streams. Now we come to the most advanced and versatile category, which is MIMD. Here we have multiple processors, each executing different instructions on different data at the same time. This is the heart of modern multi-core processors. So here we have the definition of MIMD is a parallel computing model where multiple processors execute different instructions on different data streams. So here we have the characteristics of MIMD is multiple processors working on different tasks, each with its own instruction stream and data stream. So we can have the most relatable example is, think of a team of workers, each with their own task and a data to handle. This is what happened in multi-core CPUs, where each core can handle different instruction and data simultaneously. For example, your phone's processor or a supercomputer might use this type of system. So MIMD enables today's powerful parallel computing systems for high-end servers to cloud computing. This is an important point of MIMD. Here we have some examples, that is multi-core processors, Intel i7, AMD Ryzen, like that. Supercomputers and distributed systems like cloud computing clusters. It is having high performance computing systems. So let's go to the next slide, which is the comparison of Flynn's classifications, which gives you a clear comparison of 4 types. So how SIST, MIMD, SIMD, MIST all can compare the instruction and data streams. So let us see, the first one is SIST. Here we don't have any parallelism, but processing speed is very low. Application areas are simple tasks, embedded system. Next, move on to the SIMD. We have data level parallelism and medium to high processing speed, and which is used in image processing simultaneous. Next, coming to the MIST, which is having instruction level parallelism on single data. Processing speed is very rare, and applications we are using here. This is in fault tolerant specialized systems. Next, coming to the MIMD, it is having instruction level and data level parallelism. Processing speed is very high, and we are going to use this MIMD in multi-core systems, HPC and cloud computing. So now let's look at where these categories apply. SIST is used in simple systems, SIMD in graphic heavy tasks, and MIMD is used in complex multi-core systems, and MIST could be used in the specialized applications, such as SIST is having basic tasks that do not require parallelism. It is simple computation and embedded systems. SIMD is used to image and video processing, example GPUs, and it is used in scientific simultaneous, example weather forecasting, simultaneous of physical systems, and it is used to process the audio and speech processing. And next move on to the MIST, which is used in fault tolerant systems, which is having rare applications. Next coming to MIMD, which is used in multi-core CPUs for general computing, supercomputers for high performance scientific computation, and which is having distributed systems and cloud computing for large scale processing. So coming to the conclusion, Flynn's classification helps us understand different ways computers can process data and instructions. SIST is basic, while SIMD and MIMD allow for parallel computing, critical for modern performance. MIST is most theoretical but has specialized applications. By understanding these types, we can appreciate the incredible power of efficiency of today's computer systems. So I hope you have found this is very helpful, and you might know the knowledge of Flynn's classification or how it applies to modern systems. So thank you so much.